So the initial velocity will be when t is 0. That's what you need to pick up every time they say initial, think t equals 0. So v at 0 would equal, just basically put 0 into the formula, which is 2 minus 4 equals minus 2, and put the units in because it's a measurement style question. Next part of the question is find the acceleration when the particle is stationary. So it'll be stationary when v equals 0. So rather than t equaling 0, we now want v 0. So 0 equals the same function that we were using before, times up the bottom. That's a t. So 2t equals 2, t equals 1. So that is the when we are stationary, but we want the acceleration. So to find the acceleration, we're going to need to differentiate the velocity. To differentiate the velocity, we'll need it in a form that we can differentiate it, so we'd rather it in index form rather than over. Now we could find v dash, which will equal minus 4t plus 1 to the minus 2 times by minus 1, times also by the inner derivative here, but that is 1, so 4 on t plus 1 all squared. And that's our acceleration. So acceleration at 1, which was the time that we were after, will be 4 on 2 squared, which is 4, 1, and the units will be meters per second squared. If we want to consider the behaviour for large values of t and sketch the graph, let's get more paper. So if we look at the function and consider what's going to happen as t gets really large. As t gets really large, the bottom of this fraction gets really large. And if we divide by a really, really big number, we get a really small number. What that will mean is as t gets large, we're going to get a v value of 2 because it'll be 2 minus bugger all. So that means an asymptote at v equals 2. Now, we already found the initial velocity equaling negative 2. We found out that when the velocity was 0, the time was 1. So we've got this point, and we know that over time we need to approach this from underneath. Now, being a hyperbola, there are no bends and twists and things. We know it's a hyperbola because it's a 1 on x style function. So realistically, all we need to do is join those dots together. Final part of this question is finding the so you can read it. Finding the exact distance travelled by the particle in the first 7 seconds. So say 7 is there. Distance travelled is always going to be the area under the velocity curve. So what we need to do is we need to find this area and that area and add them together. And we have to do 2 separate integrals here because it's one's above and one's below, and if I try and integrate in one go, it'll only get the overall net change in displacement rather than the actual distance travelled. So the distance will be equal to the integral from 0 to 1 of 2 minus 4t plus 1 to the minus 1. And I need to negate that one because it's underneath. I could put a negative out the front, or I could put an absolute value around it. I want to add that to the integral from 1 to 7 of 2 minus 4t plus 1 to the minus 1. Now this is going to equal minus 2t. Oh, actually I shouldn't have done that to it because this is actually an ln function. So that's going to be 4 ln t plus 1 as an integral for that, plus 0 to 1, 2t minus 4 ln t plus 1, 1 to 7, equals negative, do a nice big square brackets. Now 2 1s are 2, minus 4 ln 1 and 1 is 2, minus 0 plus, if I put a 0 in here, the logarithm of 0, a logarithm of 1, which is left over, is 0, so that'll still be all 0 there. So we've got to negate that, plus 2 7s, so 14, minus 4 ln 8, minus 2 1s minus 4 ln 2. Hope you can see that. Equals minus 2 plus 4 ln 2 plus 14 minus 4 ln 8 minus 2 plus 4 ln 2. Minus 2. 4 ln 8. ln 8 is, so that's 2 cubed. So that's actually 12 ln 2 there. So I've got 8 ln 2 minus 12 ln 2. So minus 4 ln 2 plus 14 minus 4. And that's what I think the distance travelled should be.